According to Einstein's theory, the universe is deformed by matter like a large, flexible sheet. These deformations caused by the gravity of celestial bodies are called gravitational wells. When light passes through this irregular framework, its trajectory is bent by these wells, similar to the effect of a glass lens. However, in this case, it is gravity, not glass, that bends the light. This phenomenon is known as gravitational lensing. Observing it provides insights into the components, history, and expansion of the universe. Its first measurement, taken during a solar eclipse in 1919, confirmed Einstein's theory, which predicted a light deflection twice as large as that predicted by Isaac Newton. This difference arises from Einstein's introduction of a key new element in the deformation of time, an addition to the deformation of space to achieve the exact curvature of light. Are these equations still valid at the edge of the universe? This question is being explored by many scientists seeking to quantify the density of matter in the cosmos and to understand the acceleration of its expansion. Using data from Dark Energy Survey, a project mapping the shapes of hundreds of millions of galaxies, a team from the University of Geneva, UNIJ, and Toulouse 3, Paul Savatier, provides insights. We have here our guest speaker, whose paper we're going to talk about, Dr. Isaac Tutusaus Lexa. Had his PhD in 2018 at the Institute of Research in Astrophysics and Planetology at Université Toulouse 3, Paul Sabatier, France, and he was a postdoc researcher at the Institute of Space Sciences in Barcelona, Spain, and was a postdoc researcher at the Department of Theoretical Physics at the University of Geneva. Currently, he is an associate professor at the Midi-Pyrenees Observatory, Université Toulouse, and he is interested in using data from galaxy surveys to constrain cosmological models. More in detail, interested in galaxy clustering, weak lensing, galaxy-galaxy lensing, and their joint analysis for spectroscopic and photometric galaxy surveys with the goal of constraining extended models for dark energy, dark matter, and the theory of gravitation. Um, I'd like to welcome here in Quantum Photonics Dr. Isaac Tutusaus Leksha. Isaac, welcome to Quantum Photonics.
Hello. Hi. Thanks, Cecile, for the introduction, and thank you also for the invitation. I hope you can all hear me fine. It's my very first time using Clubhouse, so I'm still learning how this app works. Perfect. I see some thumbs up. That's great. Good. So as I said, yeah, thank you very much for the introduction. I'm happy to talk today about cosmology and a little bit about what we've been doing together with some colleagues, basically testing Einstein's theory. I just prepared a bunch of slides that can hopefully guide us through the discussion. But I think from what I understood, the format is pretty free. So in case you have questions also, I mean, from my side, there is no problem at all if you just want to ask. If instead we just wait until the end for the discussion, that's also perfectly fine for me. There is no problem. So yeah, today, this afternoon is to talk about how we measure what we call the space-time distortions, and we'll describe what that is in the universe. So for example, if we go to the second slide, or just the content, I apologize in advance if there are some experts in the field. Maybe some of the things that I'll say are a bit not technical enough, maybe, but I just wanted to give a brief introduction for everyone to be on the same page. And then we'll start increasing in terms of complexity until reaching the results of the paper. But I'm also more than happy to just stay a little bit more after the discussion in case there are technical questions or you want to go into more detail in any of the points. So basically what I wanted to talk about is first to remember, everyone, that the universe is expanding and what that actually means. Then, what's the universe? What does the universe look like at large scales? And then we'll move towards already what's closer to the paper. So, what does it mean to probe the large scale structure? How do we do that? How do we actually measure these distortions? And maybe the most important question, what is next? So, what are we planning to do? What might be done with these measurements and these techniques? So, if you all go to slide number 3, this is something that's sometimes leads to some confusion. There is astrophysics and there is cosmology, and sometimes cosmology is seen as a part of astrophysics, but I kind of disagree with that statement. Astrophysics is usually basically anything related to physics beyond the Earth, but up to a certain point. What do I mean by that? Basically, if we start looking outside of the Earth and we look at other planets, stars, other solar systems, other galaxies, this is what's usually known as astrophysics. But once we go beyond galaxies, so basically we look at scales much, much larger than galaxies themselves, then we enter into the realm of cosmology. So basically the goal is to really understand the universe as a whole. So here, for example, I just put 3 images. The top left, you can see this is one of the very first images of a black hole. That was basically obtained by the EHT collaboration a few years ago, and this led to a Nobel Prize, obviously. So here we could see basically the horizon of a black hole. On the top right image, we can see an AGN, an active galactic nucleus. Basically, we can see the accretion disk around the black hole and how material infalling basically leads to these high energetic jets. Or the so famous image of the pillars of creation, where stars are born. So these are very nice images, but this is not what I, as a cosmologist, what I work on. These, we would say, these are too small scales. If instead we move to slide number 4, here we start looking at scales a bit larger. So this is a galaxy cluster, seen by, in this case, it's the Hubble Space Telescope that took this very nice image. And here we can see all these very distorted shapes. We're going to talk about what this implies. But basically, almost each one of these objects is a galaxy. So this is, I would say, maybe the smallest scales that we'll probably consider in cosmology. So we treat galaxies as little dots, or just with a small shape, let's say. We look at the shape of galaxies, but galaxy is the smallest object that we will essentially consider in practice. Okay, if we move to slide number 5, this is a simulation, this is not the real universe, but this is essentially how we think the real universe looks like. So we think that matter basically forms some kind of web, which is known as the cosmic web. So imagine that all these purplish points are basically matter particles. In this case, dark matter, but we'll talk about that a bit later on. And we can see in this simulation how these particles basically are attracted together because of gravity, and how in some regions there are so many of them. These are the yellowish points where there is a significant overdensity of these particles. So this is the type of structures that we try to understand from a cosmological perspective. Good. There are just a couple of more things I wanted to introduce in the introduction, if we move to slide number 6, which will be relevant later on. The first thing, and this is sometimes a bit striking, even for people working in astrophysics, because when we do astrophysics with planets or stars or things like that, they're all very, very close. I mean, a few light years away, but that's nothing. In cosmology, we work with objects that are much, much farther away. And An important thing is that nothing is instantaneous in the universe. And this is very interesting. I mean, Einstein already told us with his theory of special relativity that actually there's nothing that can travel faster than light in vacuum. And that means that when photons basically leave a galaxy, they will need some time to reach us here on Earth. So when we observe those photons, when we observe the light that basically came out of a galaxy a few billion years ago, we're actually seeing that galaxy as it was at that time, not as it is now. So every time we look at the sky, we're basically observing the past. And this will be important because then when we do cosmology, we're essentially studying the past of our universe. Another physical effect that's important, it's what we call the Doppler effect. And I'm sure you're very familiar with this. For example, if there's an ambulance that's coming towards you, you'll hear a higher frequency than when this ambulance is moving away. So this change of frequency, it's because the ambulance is moving with respect to your reference system. Light actually can also be modeled as a wave in the same way as sound. So there is something similar, well actually it's exactly the same effect, which is the Doppler effect, which means that if we have an object that's basically moving away from us, like a galaxy, here it's just the sun in this sketch, but imagine it's just a galaxy. If it moves away from us, we'll see its light actually redder. So it will be a bit more redder than what's actually coming out of the galaxy or the sun or any other object emitting light. And if instead this object is coming towards us, we'll see the light actually bluer. In cosmology, this is very important because we'll see the universe is expanding, which means that basically everything or almost everything around us is basically moving away from us. So it means that all the objects we'll see, their light will be redshifted. So there will be this quantity redshift. The higher the redshift, it means the farther away it is in terms of distance and the farther away it is in terms of time. So higher redshift, we're going back in time. It's just that in the universe, it's not because the galaxy is moving away. It's because the universe is expanding, which is a bit different. But the idea is essentially the same. Let's just move to slide number 7. Probably, well, I don't know if, I mean, this plot, this image here is quite famous, but if the image doesn't tell you anything, probably the name does. This is what Edwin Hubble measured in 1929. So he managed, together with other people and using the work from many people actually, to measure the velocity of different objects at that time. It was not even clear that these were galaxies as a function of distance. And he realized that actually almost everything is moving away from us. So it seemed that the universe actually was expanding. And this was almost 100 years ago. Let's just move to slide number 8. So that was the end of the introduction. So maybe you're familiar with all of the topics and it's been just a boring introduction. If that's the case, I apologize for that. But I thought it was important to clarify these points because I'll be using them later on. Let's focus on slide number 8. This is something that's far from straightforward. What does it mean that the universe is expanding? Usually we tend to see our by our universe, I mean basically what's around us here on Earth in 3 dimensions. So we just tend to imagine things in 3 dimensions and that's more or less easy. But actually, it's a bit more complicated than that. When we say that the universe is expanding, it's not just a universe within a 3-dimensional box that's expanding. It could be like the box itself is expanding. And here you have this image. This was a video, but for the PDF, I just took some snapshots. Let's imagine you have a balloon. This would be the smallest sphere here on the left. You take a pen and you draw some galaxies on top of this balloon. This would be the yellow dots. And the blue arrows, those are just photons moving from one galaxy to the other. Now, imagine that there is someone or something basically blowing into this balloon. This could make the balloon expand, right? And you can see that actually, if you look at the second sphere, that would be the galaxies, these yellow dots, are a bit further away, further apart, compared to the first image on the left. But actually, the galaxies themselves, these points, they have not moved. They haven't moved. It's the space between them that's grown. It's the balloon itself that's basically expanding. And if we continue just flowing into this balloon, then we'll get the sphere on the right. So it's something similar. This is some kind of analogy. Instead of being in a universe of 2 dimensions, like this balloon would be, we think we live in a universe with 4 dimensions, which is a bit harder to imagine. But the idea would be the same. It's not that galaxies are actually moving within the universe, but that's a different story. And we can talk about that later on if you're interested. But the idea is that the space-time itself, where galaxies live, is expanding, like the balloon is expanding. So that's what it means that the universe is expanding. It's not the universe growing inside a larger space. It's the universe itself that's growing. And if we move to slide number 9, well, if the universe is expanding, the first thing one can think of is, well, let's just go back in time. If the universe is expanding and we just go back in time, it means it was smaller. And if we keep going back in time, it was smaller and smaller. And at some point, well, the universe was a singularity. This was the origin of the universe. And this is basically the Big Bang theory. So here you can see a very nice image by NASA showing how the universe expanded as a function of time. So let's go a little bit through the different details. We can start from the left-hand side. This is called quantum fluctuations. Before that, we don't really know what happened. Mathematically, it's a singularity. The model breaks down. We do not have a reliable model, mathematical model at this point that can explain what the universe looked like. So, this is a very active field of research. Some people try to understand what happened actually right after the Big Bang, but we're not going to talk about this today. Right after this, there was a period, we think there was a period called inflation. So there was some process that basically expanded the universe exponentially, and we went from these tiny quantum fluctuations to something with a given size already. The universe was very hot at this point. So basically all particles were mixed together and we had like a plasma. But the more the universe was expanding, the more it became difficult for these particles to interact one with one another. And at some point, photons basically could really, it was hard for them to stay restricted into this plasma of baryons, photons, and other particles. So they were free to propagate. And this is what's called here as the afterglow light pattern. So basically the cosmic microwave background, this first radiation that we can see of our early universe. And then the universe kept expanding. Different things happened in the meantime. It's called dark ages. And first stars start to appear, first galaxies, first planets. And close to today, so basically on the right-hand side of the image, we are in what we call the accelerated expansion driven by dark energy, which is even more mysterious, let's say, than dark matter, depending on who you ask this question to. But this is basically what we're going to try to better understand today. And we can always ask the question, actually, of what happens tomorrow. So if we go to slide number 10, well, we know that we're coming from a universe that's expanding, it was small in the past. So actually, there are three different possibilities. First, there is the big crunch. So imagine that for whatever reason, the accelerated expansion stops at some point, and gravity is so important, then the universe just comes back to a single point, to a new singularity. And we go from the Big Bang to the Big Crunch. Then there is another option, which is what we call the Big Freeze, which means, well, the universe keeps expanding in an accelerated way, but actually, it keeps expanding, but not in an accelerated way. So its expansion slows down, but still it keeps expanding until infinite. So it's called big freeze in the sense that at some point, asymptotically, with an infinite amount of time, we would reach almost like a static universe, which is it's not exactly the case. The universe cannot be static, but with an infinite amount of time, things would almost stop moving. And then we have the big rip, which is the case where the universe keeps expanding in an accelerated way, and at some point, the expansion becomes so important that we'll just start ripping galaxies apart, ripping solar systems apart, and at the end, even ripping atoms apart and just having the essential particles in the universe. So we don't really know in which of these three cases we'll end up being. And what we try to do is basically we try to look at the past, understand how the universe evolved, and basically try to get an idea of what are the possibilities towards the future. Good. Let's move to slide number 11 then. So basically, when we look at the universe at large scales, so from a cosmological perspective, its expansion and obviously what's going to happen in the future depends on essentially two different things. One is the content of the universe, so basically what's in there, and the other one is the theory of gravity. So the first question we can ask ourselves is, well, did Einstein actually get it right? And is the theory of gravity general relativity, or is it something else? And in what concerns what's in the universe, well, we know there is radiation, and that's easy because we can see light coming from the sun, for example. So we think we understand radiation. There is baryonic matter, which is basically all matter we can see here on Earth, the matter we're used to. And let me just mention something, make a quick parenthesis here. You can see that I put electrons within parentheses as baryonic matter. And you might say, well, but electrons are not baryons, and I agree. But this is something, it's in some kind we're abusing language a little bit in cosmology. Everything that's not dark matter, we just call it baryonic matter, even if they are not baryons, because baryons are the most relevant thing in terms of cosmology. So even if we neglect some electrons, that doesn't really change much. So these two are well known, but then we think that there might be something called dark matter. We think there might be something called dark energy, and maybe there is something else. So there are still a lot of things that we need to better understand. Let's just move to slide number 12, and let's start with gravity. So what Einstein told us with his theory of general relativity is that objects, and that includes light, even if it doesn't really have mass, are not really attracted because of a force. So gravity is not a force. Basically, when we have something massive in the universe, that will deform space-time, and the massive and light, so the massive objects and light actually travel through this deformed space-time. So basically, this is the plot, well, the image you can see on the right-hand side. Imagine you have the sun here. The sun is massive, so it will deform this grid, which is supposed to mimic the space-time. And if there is light coming from a point B that was in principle supposed to travel following a straight line to the Earth, because of the sun, we will see this light as if it were coming from point A. So basically light will be distorted. And this corresponds to the gravitational wells that Cecile was mentioning at the very beginning. Basically, when we have massive objects in the universe, they will deform space-time through some gravitational wells, and then all objects, either massive or light, will have to move through this deformed space-time. So these are the measurements, these are the space-time distortions that we will try to measure and that we will discuss today. Let's move to slide number 13. Well, I asked before, did Einstein got it right? This is what we try to understand. Well, it's interesting to know that there are tens or even hundreds of alternative models already right now in terms of gravity from a cosmological perspective. And this is just a summary of some of them that was made by Tessa Baker. Some of the modified gravity options that we have nowadays. So for example, you can add additional components into the universe, or you can add additional dimensions. And there are models that are more or less theoretically motivated. But actually, general relativity still agrees very well with observations. So we are a bit lost in that sense. Meaning, we have a theory, which is general relativity, that works very well. And we have many options to go beyond general relativity. But since general relativity is actually not failing, we don't really know where we should be looking at to test new models. Then I just wanted to briefly introduce dark matter and dark energy, because they will be important to fully understand the measurements that we'll show you at the end. Dark matter, what is it? Well, we don't really know. What happens is that we have some observations that suggest that actually there is more matter in the universe than the one we can see. For example, this is an image from a galaxy cluster, and you can see these very distorted shapes. Galaxies do not look like this. This is not physically motivated. What happens is that these galaxies are very far away, and there is a huge overdensity in front of us, this cluster of galaxies, that basically deform space-time in a very significant way. So there is a very significant gravitational well here, and when we observe galaxies that are behind the galaxy cluster, their images are very significantly distorted. So what we've done is we've derived the amount of matter that should be, for example, in these objects in order to generate such a distortion. And we've realized that actually we need much more matter than what we can see in this image. And this is just not the only evidence. We have many evidences suggesting this. And the question that we can ask ourselves is, okay, we think there is something called dark matter. Question, is it important? Well, yes. First, because we think it constitutes roughly 25% of what's in the universe in terms of energy right now, which is a significant fraction. But what's even more interesting, it's what we call the skeleton of galaxies. So this is what I'm showing in slide number 15. So you can see this pie where roughly 31% of the universe is matter. And from this 31, we think roughly 80% is something known as dark matter. And the other 20% is the regular matter we can find in stars, galaxies, or dust and gas. So if we just move to slide number 16, I like this image very much. This is a simulation, it's not real observations. But here we can see, remember at the beginning I showed you the filaments and the structure of the universe, how we think it looks like. This is the same thing, but this is what we call a hydrodynamical simulation. So it's a simulation including both dark matter and baryonic matter. And if we look at this small region that's zoomed in this white square, and then we can zoom in again, and we look into a region where we have an overdensity of dark matter particles, you can see that's where a galaxy is actually being formed. So this is a simulation where we just put in dark matter and baryonic matter particles, and we let the simulation evolve as a function of time, like the universe would do. And we see that galaxies tend to appear when we have overdensities of dark matter. So basically, by using galaxies, we can trace where our dark matter is. Good. Let's just move to slide 17. There is something else that's dark energy, which is even more strange. So dark matter is supposed to behave as matter, but we call it dark because we cannot observe it. But then there is dark energy. And you might remember at the beginning when I said, let's assume the universe is expanding. Let's assume we consider a balloon to have an analogy with the expansion of the universe, and we blow into the balloon. Well, that first blow, that could be the Big Bang. But at some point, the balloon will tend to go back to the original state because gravity is attractive. And actually, we realize that no, it's expanding in an accelerated way. So it's if like there was something still blowing into the balloon, basically increasing the expansion, keeping the universe expanding, and the more time goes by, the faster this expansion becomes. So there's some kind of energy that's still pushing and generating this accelerated expansion, and we cannot actually observe that. So that's why we call it dark energy. Yeah, I think I'm just gonna skip this. If you have questions about dark energy, more than happy to talk about this afterwards. But actually, for the main point of today's discussion, maybe this is not entirely needed. So I'm just gonna move to slide number 18. Good. So, question again: is dark energy important? Well, we think it constitutes roughly 68% of the universe. So I would say yes, it's pretty important. What happens is that we don't really know the nature of this component. We don't know if it's a cosmological constant that was first introduced by Einstein himself, or if it's a new component, it's something new in the universe. What we do know is that it's actually dominating the expansion of the universe today. So it's really one of the more interesting questions in cosmology right now. What actually is dark energy? Let's just move to slide number 19, and we are entering the last part of the presentation. For cosmologists, it's very important to probe both the expansion and the large-scale structure of the universe. Why? Because this provides a lot of information on dark matter and dark energy. For example, let's just pick this image from a simulation here, where we can see again all the filaments, all the cosmic web. If we have more dark matter in the universe and less dark energy, we know that dark matter will act as matter, so it will help basically get things together and get more structures. The more matter we have, gravity is attractive, the more structures we should have. If instead we have less dark matter and more dark energy, then the expansion will be more important, so it will be more difficult to generate this type of structures. So that's why we are so interested in basically probing this large-scale structure, because this provides direct information on the amount of dark matter and dark energy, and also on their behavior. So we can understand, we can infer properties of these dark components of the universe by probing the large-scale structure. And that's why cosmologists have basically spent a lot of time building what we call galaxy surveys. So here, for example, on the left-hand side, you can see the dome where from which the dark energy survey was carried out. And on the right hand side, you can see just an image of this survey. So all these little dots or small circles are basically galaxies, and there are a huge amount of them here. And as Cecile said at the very beginning, we basically use more than 100 million of these galaxies to perform the analysis that I'll show you in a bit. Before that, let's just quickly move to slide number 20. I wanted to emphasize once again what gravitational lensing is. So we saw the schedule of the sun and basically distortion of space-time, and that basically light does not follow a straight path anymore, but a curved one. Okay, let's just go one step further. Let's just look at gravitational lensing, but at scales of the entire universe. So this is what we do. We have some galaxies that are very far away. This could be the green galaxies on the left-hand side, what we call background galaxies with original shapes. These are the true galaxies and how they look like. Then let's imagine that we are on the right-hand side, and actually in between there is no vacuum, right? I mean, there's something in the universe between the galaxies that are far away and us. Most, in general, just more galaxies. These are what we call the foreground galaxies. And galaxies have a mass. So these galaxies will, each one of them, introduce space-time distortions. So they will modify space-time in the universe, which means that light coming from these background galaxies will be distorted. So when we observe galaxies in the sky, we do not see galaxies as how they are. We see these distorted shapes. And the distortion depends on basically what's in between those galaxies and us. So by studying how galaxy shapes are distorted, we are essentially probing everything that's between these galaxies and us. So we are probing the large scale structure. And that provides us information about all the mass distribution that there is along the sign, the amount of matter, and also other things like how structures grow as a function of time. So this is why we use gravitational lensing in cosmology. We do not focus on a specific object. We take hundreds of millions of galaxies and we study how their distortions behave to infer basically what's in between those galaxies and us. Okay, we're now really reaching the end. I just have 26 slides and we are slide number 21. Let's just go directly to the results of the paper. We measured these distortions of space-time. How? Well, there is something that's called the Weyl potential. I will not enter into the technical details, but basically it's a mathematical quantity that can, that encapsulates both the temporal and spatial distortions of the geometry of the universe. So basically again, here you can see the image of the sun and the gravitational well, how it distorts this grid, but this grid is in 2 dimensions. In practice, we have 3 spatial dimensions and the time component. So basically we have both the temporal and spatial distortions, and we're not just looking at the distortions introduced by a massive object like the sun. We are looking at distortions introduced by the entire cosmic web. So imagine there are galaxies behind the cosmic web that you can see here on the right-hand side, and you're looking at these galaxies through this cosmic web. The Weyl potential basically encapsulates all the spatial and temporal distortions introduced to the geometry of the universe because of this cosmic web. This is what we try to measure. And if we go to slide number 22, you can see the results. Well, actually, the new thing we did is we developed a new technique to directly measure how this Weyl potential quantity evolve as a function of time from the observations. So instead of assuming a model, like for example, general relativity or one of the tens or hundreds of alternatives, we just looked at the data, we looked at the observations, and we asked them, what's the type of evolution of the gravitational wells that you need to explain the universe? And this is what you can see in this image. So here in this figure, you see the evolution of this Weyl potential as a function of redshift. If you remember at the beginning of my presentation, by redshift I mean, so basically the higher we go in redshift, the further we go back in time. So if you look at the last point, which is close to 0.8 in redshift, if I'm not wrong, I think that's something like 7 billion years ago or something like that. And you can see two different things here. You can see a gray band with a black line. That's the prediction from general relativity. And you can see these blue dots with some lines. That's basically the dot is where we measure this quantity to be, and the line is basically the uncertainty around this measurement that we estimated. And you can see that if you go to high redshift, well, the second to last point, for example, the blue dot agrees with the black line within the uncertainties. So you would say, yeah, the measurements are compatible with general relativity. And if you look at the last point, well, they do not perfectly agree, but they are not too far. But if you look at the first 2 points, and well, actually you go to slide number 23, you can see that there's it starts to appear like a discrepancy. So what we can see is that the measurements of the Weyl potential at these low redshifts are significantly smaller than what's predicted by general relativity. So the gravitational wells that we've been mentioning a few times now already, we've mentioned a few times, appear to be shallower than what general relativity actually predicts. So question is, does this kill general relativity? No, because we can see that the points are not compatible with the prediction of general relativity, but the uncertainties are still sufficiently large as to think that maybe it's just a statistical fluctuation. Maybe just out of chance that we got shallow gravitational wells, and actually general relativity is still the theory of gravitation. So then the question is, what next? And that's slide number 24. In here, to get these measurements, we use the dark energy survey. So that's basically roughly a bit more than 100 million galaxies that we used for this analysis. But there are new surveys that have started already, actually. One of them is the Euclid mission. So this is a space satellite by ESA, the European Space Agency, and the satellite is already taking observations right now. If you look at slide number 25, this is the first 1% of the observations that will be taken by this satellite. So there are a lot of things to say in this image. If we start from the top left, that's the image of the entire sky. And there are 3 different things that are shown in here. First, there is a map showing stars from the Gaia satellite. There is another map showing all the dust from the Planck satellite. And there is this small region here in yellow. That's basically where we can see zoomed in. This is the first 1% of observations of the Euclid satellite that will observe a huge amount of galaxies with an amazing resolution. So here, for example, you can see that we can zoom in even 600 times and we can still resolve galaxies interacting at basically the first stages of the universe. So in just this image, you can see here, there are roughly 14 million galaxies that we can use for cosmology. And Euclid is expected to measure roughly 1.5 billion galaxies. So with Euclid, we expect to be able to perform these measurements with much more precision, and that hopefully will tell us whether we still see a deviation compared to the theory of general relativity, or if it was just lucky statistical fluctuation. So just to conclude, I wanted just to mention a few things. Well, cosmology has become a precision science. So many years ago, maybe it was more kind of, I mean, not philosophy, but maybe it was not as quantitative as it can be now, because now we have amazing measurements and we have very powerful theoretical models. So we can actually perform this precision science. I just want to say, when we say cosmology, cosmological analysis, it's not just cosmologists that actually work on this. We need theoretical models. So means we need theoretical physicists and mathematicians that actually build the cosmological models of how the universe should behave depending on what we put in it. We also use observations, as I showed you. That means we need a lot of engineers, we need a lot of experts in image, in data processing. And then the key point is that we need to compare these models and observations to check basically which models work, which models agree with the observations and can explain them, and which do not. So we also need experimental physicists, mathematicians, engineers, and given the amount of galaxies that I was talking about, 1.5 billion, that means we need also to rely quite a bit now in artificial intelligence, big data techniques, all this type of analysis. And even if I showed here these results, it's important to keep in mind that these analyses are so complex that we actually need a lot of people involved to make them successful. And that's why these, especially the latest surveys, are basically being done with international collaborations with hundreds or even thousands of people, each one with their own expertise. So just to finish, yeah, I think there is still a lot of work to better understand our universe. And we still want to know whether Einstein was right or not with his theory of general relativity that was proposed roughly 100 years ago. Hopefully with the newest data sets, we'll get a clearer picture. But for the time being, this is very exciting. And we look forward to continue studying this. Yeah, I think that's all I wanted to say. And I've been talking for much, much longer than what I expected. I thought this would, I was expecting like half an hour, something like that, but I see it took a bit longer. Apologies about that. I don't know if you still have any question or you would like to have any discussion at this point.
Yeah, thank you so much, Isaac. It was a very systematic presentation. In fact, people from the general audience would be very well guided about your presentation and the journey towards your going to the conclusion, and of course, the data that you showed in the survey that you made. So I think it's great pedagogy. So we don't care if you think that it had gotten long, but this is one of the most systematic presentations that I have ever seen. So thank you so much for being a great pedagogist. And we'd like to inform the audience that we are now opening the floor. If you have questions, please feel free to raise your hand. We will bring you up the stage. So in the meantime, I would like to ask Isaac about the survey scope. How does the dark energy survey gather data on such vast scales, and what are its main advantages over the previous survey?
Yeah, that's a very good question. So usually what's done is, well, we have two types of surveys. Either they are on Earth, meaning we have a telescope here on Earth, and that implies that if the telescope is in the northern hemisphere, then we'll only be able to see the northern part of the sky, and if it's in the south, then the corresponding southern part. The Dark Energy Survey, for example, is in the south, actually is in Chile, and what was done was to basically select the region of interest for cosmological analysis. So they selected roughly 5,000 square degrees, which is about 1 octane of the entire sky. And observations were performed there to basically detect all types of galaxies and even other objects like solar system objects, plenty of different things for astrophysical and cosmological purposes. Then it was already a major improvement with respect to what we had before, because it was the very first time that we had a few thousand square degrees and hundreds of millions of galaxies to work with. And if we move to the next step, which would be the Euclid satellite, for instance, then we are going one order of magnitude or even more above that, meaning with Euclid we expect to observe essentially almost all sky, except for the galaxy, which is not very useful for cosmology because there is too much dust, stars, and things that we cannot really use. But everything that's outside of the galaxy and the ecliptic plane, which is what's called the dark sky, will hopefully be observed with Euclid. And Euclid can do that because Euclid will be in space. It's a satellite, so there's no problem then. And we'll move from a few 100 million galaxies to basically 1.5 billion, something like that. And on top of that, technology has improved since the Dark Energy Survey was built. So also the measurements will be much more precise.
Yeah, thank you, Isaac. I have one more question then. We have Agnostic who came on stage and Kevin, and plus I think there are also questions on the room chat. Just one more question. I'm very curious about the model independence. You mentioned that the measurements are model independent. Why is this a breakthrough for testing theories of gravity?
Right, that's a very good question. So there are two different ways to do things when we want to test gravity, for example. One is to say, let's just pick a model. You can choose your favorite model. For example, you say, well, I do not like general relativity. I want to choose a model where instead of 4, I have 25 dimensions, and I want to work with that. That's perfectly legit. What you would do in this case is you would perform your entire cosmological analysis with this model. So you take the model, you compute how the quantities that can actually be observed should look like within this model. And once you have your predictions, you compare them against the data. And two things might happen. You can either see that it works or that it doesn't. Then if it works, that's great. We found a model that can explain the universe. If it doesn't, we need to start over, meaning we need to choose a different model, recompute how our observables will look like for this model, redo the analysis, and wait to see whether the model can explain the observations or not. If you do a model-independent approach, the nice thing is that you are already kind of testing families of models. In this case, we were not even testing a family of models. We were just asking the data, what's the evolution of the gravitational wells that you need? And we got these measurements. Once you have the measurements, then you can compare, like we did in the image I showed you, against general relativity. And we see that it doesn't work that well. But we could also pick a different model now and just compare how gravitational wells should evolve within this model with the measurements that we got. And if we see that in this case the model works, there is no need to redo the entire analysis. We just showed that this specific modified gravity model of 25 dimensions, for example, can explain the observations. Actually, in the paper, we did do that for two different types of models. I think there was one of the Ondesky family, or a couple of them, and another one using a parameterized approach. But the idea is this one. By using a model-independent analysis, we got these new measurements, and now we can compare different models against them without the need of actually rerunning the entire analysis for each and every one of the models.
Yeah, thank you so much, Isaac. There is a question by Axe Newborn at the room chat. I just would like to address this because he was the one who asked the very first question while you were lecturing. Can universe expansion effects be seen in scales like solar system or inside the Milky Way galaxy?
Right. In principle, it could. So in practice, given the universe that we live in, the impact of the accelerated expansion, so the impact of the dark energy, is negligible at these scales. Meaning, in systems that are gravitationally bounded, like for example the solar system, where planets are basically orbiting around the sun, or even the galaxy, where we are all orbiting around the central black hole, the existence of dark energy in the universe um, is negligible compared to the gravitational force, to the gravitational interaction. So we cannot really do anything. So there is no risk of basically uh, destroying the solar system or the galaxy because of the accelerated expansion. But this is with the concordance model that we have today, right now, and the one we think it's closest to the observations. But if you remember the image I showed, where we see the future and we have different scenarios, there was one called Big Rip. So if the energy was so important that just kept expanding the universe even more in the future, it could happen that at some point we could start seeing the effects of that energy at the galaxy level, and then even at the solar system level, and continuing until the basically the elementary particles. But if we look at the observations right now, what they tell us is that we are not at that point. So dark energy is only relevant when we look at very, very large scales, the cosmological scales.
Yeah, thank you. So, we will now go to agnostic and after that to Kevin. I think, there were two people raising their hands. We're trying to bring them on stage. I think it's Elle and Chavis, but I don't know why they are not on stage. We already tried to bring them up. If that's the case, probably you should go out of the room and come back again so that you can go up the stage. So I'd like to thank Agnostic for waiting patiently. I'd like to give the mic to you now if you'd like to speak, Agnostic.
Yeah, I have only a generic question. Yeah, thanks, Isaac, for participating in this session and providing your insights. And thanks, Cecile, for conducting this room. So, just wanted to understand how. This is a generic question. I'm sorry if I'm not, if I have not asked any questions with respect to what you have presented, because I'm a novice. So when we are still exploring how correct Albert Einstein is, so in 1930s or 1940s, he might be. I mean, he is still considered as one of the greatest minds. But do we have scientists as capable as Einstein right now? Uh, that's my question, Isaac. Yeah, thanks.
Yeah, I mean, I think Einstein was, I mean, well, there's no discussion, right? He definitely was a genius. The amount of things he did in so many different fields, well, that's just impressive. There are no words for that. I do think there are cosmologists that really are extremely good. Maybe one famous example, which although was not exactly cosmology, but I mean Stephen Hawking did also an amazing work in terms of black holes and also his contributions to the Big Bang Theory. Um, the proof also, I think, well, proof, an argument justify that I think there are very bright minds in cosmology is if you look at the amount of Nobel Prizes that have been given in the past 10 years in physics, a very significant fraction of them have been given for cosmological results to cosmologists. And I think there are very bright minds behind some of the latest results. It's true that when you say that the standard model relies on general relativity that was predicted by Einstein 100 years ago, might seem a bit surprising. We might wonder, well, actually, is that because there are no other theories that have been proposed? And actually, there are. There are many different alternatives or extensions. It's just that until now, general relativity has worked so well that it's not been really justified to use another theory. It's a little bit like if you look between Newton and Einstein, I would say. Newton proposed his theory of gravity, and we spent several hundreds of years just using that until Einstein came. And there was actually no reason to stop using Newton. We saw a particular case where Einstein could explain the observations and Newton could not. So I guess we're looking for something similar here. We're looking for observations that some extended theory, some modified gravity model can explain, but that cannot be explained within general relativity. And that would really be a breakthrough. We would have information to understand where we should be looking at. And I think, yes, to go back to your question, I think there are very bright minds. I wouldn't dare comparing to Einstein. I think that's not the goal. But yeah, I would say there are very, very bright people behind most of the analysis, and hopefully, well, it would be very exciting to find something soon. Yeah.
Yep. Thanks, Cecile. Yeah, I'm done here.
Yeah, thank you, Agnostic. Yeah, I'd just like to ask Bob or anyone on stage. Now I see Agnostic, Kevin, and Ash, and I think we tried to bring up two people who raised their hands. Are there more people on stage that I cannot see aside from Agnostic, Kevin, and Ash? Bob?
No, that's what I've got.
Yeah, so once again, I'd like to tell those who raised their hands, we tried to bring you on stage, but you're not here. So we advise you to go out of the room and come back so that you might be able to go up on stage. So anyway, I'd like to pass the mic to Kevin now.
Oh yeah, hi. Yeah, yeah. This has been very thoroughly, presented by you. Like Cecile said, which is just incredible. I think so clear. So some of the things I can think of is do you think this discovery, may impact like our understanding of gravitational waves and their detection? Is my first question.
Mm, yeah, that's a good question. So the thing is that let me just start again. We know that the theory of gravity should be unique, meaning it wouldn't make sense to have a different theory of gravity for the gravitational waves and for cosmological scales. So the universe is there's just one universe. So ideally, we should be able to find the theory of gravitation. In practice, well, in physics, we don't really know the truth, right? We don't really know the true universe. So what we try to do is we come up with models that can explain the observations, and the more observations we have, the more we try to improve our models to explain what we keep observing. So now what we saw is that there appears to be some kind of tension with general relativity. We saw this with a specific data set and a specific cosmological probe. So we use gravitational lensing for this, and we use this specific data set containing these galaxies to perform this analysis. Till now, people that are basically looking at gravitational waves, they have not found any deviation compared to general relativity. So general relativity can explain very, very well gravitational waves, at least as they've been observed until now. So in order to say, okay, this model is no longer valid, I would say we would need to have to gather a bunch of different observational proofs and support such a claim. So for example, if we wanted to say general relativity is no longer the theory of levitation, should be something else, it's just not enough to show that for this specific data set with gravitational lensing, it doesn't work. We should also check whether there are problems in other fronts, like, as you mentioned, gravitational waves. And if, for example, we came up with an alternative, imagine we get the Euclid data and we confirm that general relativity cannot explain these observations. Well, then we would need to come up with an alternative model that could explain the observations. And then it would be very interesting to see what this alternative model tells us about gravitational waves. So the two of them are linked, I would say. One cannot actually do things without the other because the universe is just one. And let me just finish my reply by mentioning something interesting. You might know that we've detected just one single event, but in one case we detected both the gravitational wave and the electromagnetic counterpart. So basically we could both hear and see the collision, basically, of the compact objects. And with that, we inferred that the speed of propagation of gravitational waves is essentially the speed of light. So from one day to the other, that essentially killed half of the models beyond general relativity. So we had a huge family of models that were potential alternatives for general relativity, but that were actually predicting a different speed of light, so a different value for the speed of light and the speed of gravitational waves. And when we actually measured that the two of them should be equal, that removed a huge amount of models from the literature. So indeed, I think it makes sense if we can confirm that general relativity struggles to fit these measurements, and we come up with an alternative, we should also look at what happens if we look at other probes like gravitational waves.
Okay. Yeah, that's a lot to look into, and it's very exciting that how you verified all this, of course. And yeah, so I was thinking of if this could affect GPS systems, but also another question maybe do you think this may have implications for understanding of behavior of matter in extreme environments? Is another thing.
Yeah, so for the GPS, I think there should be no problem in the sense that we've tested general relativity at the solar system scales and it works extremely well. So if general relativity is not the final answer, it should be something that at the solar system scales basically produce almost the exact same thing as general relativity because it works very, very well. So when we say modifications, I think it's more in terms of at the cosmological level. So really objects that are very far away from us. And in terms of how matter behaves, that's, sorry, I'm just laughing because that's actually what we're working on right now. We are actually using this type of measurements to study how dark matter particles behave and whether they behave in the same way or not as regular matter. So yes, there is useful information in there, and now we're working on trying to extract as much as possible of this information. So this is just here we got the measurements, and now we're trying combine with all observations and trying to test different hypotheses to basically understand a bit more of the physics. But yeah, this is definitely interesting.
Thank you, Isaac. So, Bob, can you read some questions by Chavis on the room chat since, yeah, he is not on stage. So,
Sure thing.
yeah.
For some reason, we're not able to bring him up. I don't know why. But his first question comes, what causes the wheel potential to be lower than expected?
Yeah, that's a very good question. At first order, I would say we don't know. Meaning, definitely, we cannot use general relativity anymore because we've seen that general relativity cannot really, well, struggles to explain these measurements. So we need a modified theory where gravitational wells will evolve slower compared to general relativity. What we did in the paper, for example, was to test different models, and we could see that some Ondesky models, where these are models with many additional new components, could actually explain these observations. But I would say, yeah, let me just mention something. Just make a quick parenthesis here. I would say there are two different ways to compare theory and observations. One is to use a theoretical approach, meaning we choose a specific model where we understand very well what's going on. We clearly specify what's in the universe, how things interact. We use this model, we compare our predictions for the observable quantities, and then we compare against observations. The alternative is to use what we call a phenomenological model, where we use a theory that usually works pretty well, like general relativity, for example, and we introduce some degrees of freedom. So we allow the theory to go beyond, but it's not really physically motivated. We're just testing whether the data would like to have some variation with respect to the model that we've chosen, like general relativity in this case. What we see is that the data does prefer to change from general relativity. Now the question is, what are the physically motivated types of models that can actually explain these observations, such that we can assign a physical meaning to this decrease in the wire potential. And this would be, I would say, the next step. So for the time being, we just looked at the data, we measured the wire potential, we saw it was slower than expected. Now the goal would be to try to focus on specific models where gravitational waves evolve slower than how they do it in general relativity. Then if I had to specify a physical process right now that could explain this, I don't really know. I would have to think about this and see what type of models could generate such a variation. But yeah, I would say, I mean, definitely this is very interesting, and these are the type of questions that we're trying to address now.
Yeah, thank you, Isaac. I think Chavis has several questions here. So, but in order to give a chance for others to speak, I will just ask his latest question. How does modified Poisson equation by incorporating the mu and the sigma would solve this problem?
Right. So that's exactly the phenomenological thing that I was mentioning, right? So you take the Poisson equation. Poisson equation is basically linking the psi potential, so the temporal distortions of space-time to the density fluctuations, and then you have the Lansing equation that does the same thing for the wire potential and the density fluctuations. And if you go beyond general relativity, and you use a phenomenological approach, you can use the so-called mu-sigma parameterization, where you introduce mu into the Poisson equation and sigma into the Lansing equation, and you ask the data, do you want actually something compatible with GR, with general relativity, or not? What we did is actually very similar to this, but it's not exactly the same. What we did was also to parameterize basically these equations with some free parameters that we measured. The thing is that when you do the mu-sigma parameterization, well, here we'll enter into some technical details. But basically, when you do the mu-sigma parameterization, you need to rely on Euler's equation to go from Redshift space distortions measurements to constraints on mu. And you also need mu when you want to constrain sigma. Mu also enters into the play. Instead, with our parameterization, we can directly measure the evolution of the Weyl potential just with Lansing measurements. So we rely on less assumptions, I would say. And on top of that, in order to go from Redshift space distortions measurements to these constraints on mu, you need to solve a differential equation. And for that to happen, you need to specify how mu evolves as a function of redshift. So there are more assumptions in there. And instead, we do not assume any redshift dependence. We just measure things where we have our observations. So that's why we were able to get these 4 different measurements at different redshifts, because we just measured things where we had our data. So I would say, summarizing, our approach is a bit more model independent, a bit more general. But when we limit our approach to the mu-sigma parameterization, which is something we also did in the paper, we are supposed to get compatible results with what you get if you directly use the mu-sigma parameterization, and we check that. So basically, once we have our results, we can assume again the hypotheses, the assumptions that are assumed in the standard mu-sigma parameterization, and we recover those results. So I would say we go one step further by using a more model-independent approach that can be more easily used to test other modified gravity models.
Yeah, thank you, Isaac. So we'd now like to give the mic to Ash. Thank you, Ash, for patiently waiting.
Thank you, Cecile. Thank you, Dr. Isaac, for a wonderful presentation. If I get, I mean, I find this really amazing because I feel like it's almost like we were flying blind without some of these observations, and now we have something to at least test against. So I love that it's kind of independently observation driven, and I think that, I mean, obviously that's going to take things far. My other comment is so the topology almost of the line of sight, if you want to say, is represented by the variation in redshifts, and that is affected by the dark matter, dark energy, and gravitational wells, more or less, yeah?
Yeah, so I would say that, so there are 2 things. One is space-time itself, and the other one is what's the content of the universe, what's in the universe, right? And it's a bit tricky in the sense that, I mean, the key is in Einstein's equation. So if you look at Einstein's equation, you have an equality between 2 different things. One contains space-time, and the other one contains basically the components of the universe. So the components, in this case being dark matter, dark energy, will perturb space-time. So we'll introduce, if you have matter, for example, this will introduce some gravitational wells. So this will distort space-time. The thing is that these elements, the content of the universe that introduce the distortions, they are also living in this distorted space-time. So the two are linked somehow. So if you look at the topology of what's along the line of sight, in principle, I would say it's supposed to be, if you take general relativity, for example, it's supposed to be and given, if you take general relativity and assuming the standard model of cosmology, so what we think it's the closest to observations, it should be a flat space-time. But every time you have matter, like galaxies or anything along the line of sight, they will introduce perturbations into this flat space-time through some gravitational wells. So yeah, the topology is given by your theory of gravity in this case. General relativity that tells you it should be this type of space-time, and then matter will introduce distortions that will affect, that will change basically space-time itself. Yeah.
And is it helpful to think of these spots or variations of I don't know what to call them, but inflationary slash deflationary bubbles of spots in the universe along the line of sight, and how that interacts with the gravitational waves, if it does?
I'm not sure I fully understand what you mean by these inflationary spots.
So, so in your analysis, there are parts of the universe that are more inflationary than others.
You mean parts that are more, so you mean regions that are contain more structure, more matter, that have overdensities, and regions that have underdensities?
Mm-hmm. Yeah.
Okay, yeah. And your question was, sorry, once you have these regions?
So once you have these regions, how does each region, are there, how does the inside of that region affect the gravitational waves around that region?
Oh, yeah. Yeah, they do. I mean, gravitational waves are waves that actually, by definition, somehow, almost, they propagate through space-time, right? So if we have perturbations through space-time because we have some overdense regions introducing some gravitational wells, or we have underdense regions, that will change the space-time through through which the gravitational waves propagate. So that's also one source of information. So by looking at the propagation of gravitational waves, we can also get an idea of the content in the universe. It's I would say it's second order though, because these are small perturbations, so it's not trivial to identify. So at first order, in terms of cosmology, gravitational waves are very good distance indicators. So they provide the distance, and that gives us an idea of how the universe expands and how distances behave in the universe. In terms of these how these space-time perturbations impact the propagation of gravitational waves, this is what we call the lensing of gravitational waves. And this is a field of research indeed. It's just that it's much harder. And as far as I know, I mean, I'm not, there might exist. I'm not aware of any results with real data yet. I know people have been working on these and preparing future experiments. There's potentially a lot of information to be extracted from there, but unfortunately, I'm not an expert on the field, and as far as I know, there hasn't been any results with real data yet. But yeah, this is I mean, looking into this should be interesting.
Okay, and if I can, just one last question. What are your thoughts on future strategies in terms of locations of, you know, points that you want to study further and zoom in? And, if you want to, for example, do a comparative analysis and do like okay, so we have two of these very similar topological lines of sight in a way, if you want to think of it that way, and they're very similar. And what are the changes? What are the differences between them? What's the deltas? And what would be your strategy moving like?
Hmm. Um, yeah, it's a bit complicated because the problem is that our models, our theoretical models, I mean, they cannot predict where overdensities and underdensities are. Meaning, I take any line of sight, so I look at the sky somewhere, and we cannot really predict what should this line of sight look like. What our models predict are statistical quantities. So basically, we compute, we can get an idea of how feasible it is to get such a distribution of lines of sight or not. And all the analysis comparing against the data usually are done statistically. It's true that you can focus on a patch of the sky, for example, and look at how much mass there is along the line of sight in a given point, and the point next to it, for example, and all that. But that's those are the observations. So that's fixed. The universe, it's like it is, and that's it. But once you compare against your model, you need to perform this on a statistical basis because the universe is just a realization. So this is the universe that we had. But if you pick any model, you can generate plenty of possible universes depending on how you set the initial conditions of the universe. So I would say if we had to, so for cosmology, the most important thing is to have the largest possible area with the largest amount of objects in that area. Because the more objects we have, the more signal we can extract from the measurements, and the comparison is a statistical comparison. I think then there are some things, some funny things like for example, what's known as the cold spot. So apparently there is a region in the sky that if you look at cosmic microwave background data, it's a bit colder than expected, and also it seems there is some kind of void in that region. So there are some places in the universe, in the sky, I mean, that might be interesting. But everything that I presented today would be more from a statistical perspective, looking at the universe as a whole, not really looking at a particular direction.
Yeah, thank you, Isaac. So I think there were two new people who raised their hands. Yeah, I think it's Chavis again and also Asia. But yeah, oh, Asia was able to make it as a speaker. So yeah, I'd like to pass the mic to you, Asia.
Thank you so much, Cecile. I always appreciate coming here, and this was very well put together. Not performance, excuse me. I have my notes because, yeah. Okay, one thing, listening to your description of the elements passing through the widened paths of older stars, that was kind of the visual I was getting. And I couldn't help but visualize kind of even a pebble dropping into a still lake and rippling outward, shifting everything else in the pond. And like that image, it brought the whole thing home to me. And, you know, you really have a gift for making these concepts that are beyond my purview, just very easily digestible. Um, Thank you. This was amazing. I do have one more question. There was a presentation here on time crystals, and I'm not an expert, but I like to connect the dots sometimes. And something about how their states changed. Um, I'm wondering if there's a connection between that and the shifts that were mentioned in this presentation. Would they indicate
Um,
somewhere?
yeah, well, first of all, let me actually thank you and all the other people that asked questions for your very nice words. I mean, I really appreciate it. Um, in terms of, yeah, I don't really know what these time crystals refer to, so I'm afraid I will not be able to provide a very useful answer to your question. The only thing I can add is in terms of shifts, the redshift that I was mentioning. This is naively, so without knowing what these time crystals refer to, I would say probably it's not the same thing because this shift is really just um, because of the expansion of the universe. So it's
I
the same idea
apologize.
of
It's a terrible way to introduce that question without any context behind it. Um, like
no, no,
basically,
no.
yeah, just particles arranged in a repeating pattern, not just in space, but in time. It was a really interesting
Hmm.
presentation here in this room. That's why I love this room so much. Just the things that get into your head. Um, but yeah,
Yeah, no, it's interesting. Yeah, I'm not familiar with this. I think it's not the same because the physical reasoning behind these shifts is like the ambulance analogy that I used. Is really just a fact that um, if you have an object moving towards you or away from you, that will basically change how you perceive such an object. It's just that instead of having the object moving in the same space, it's the space-time itself that's expanding. But in practice, you see that object is moving away. So that will impact how you observe the object. And it's linked to time in the sense that the problem is that once you emit light needs some time to reach us. If galaxies were much, much closer to us, they could still be redshifted. Well, actually, we do have galaxies that are much closer to us and that are redshifted, and there would be almost or less time variation, let's say. The thing is that in cosmology, since we look at objects that are so far away, and that since the universe is expanding and in an accelerated way, these objects are moving away from us at incredibly large speeds. If we were to make the analogy, so that implies redshifts that are very large, and that means that physically those objects are very far from us. So light takes a lot of time to reach us, and therefore when we see them, it's like if we were going back in time. So, but I think it might not be the same thing as these time crystals, but yeah, definitely in all science is very interesting, right? And at the end, I like something you said, connecting the dots. Um, the universe is the same for everyone, right? I mean, and that's also a problem in cosmology. We do have our models, but we know, for example, that general relativity and particle models of quantum mechanics do not get well or are difficult to put together. And at the end, ideally, we would like to have a model that could explain everything in the universe we live in. So we know there are still things to understand.
thank you again. I appreciate the time you took to consider that.
Thank you, Isha. Thank you, Isaac. So, Isaac, we've been here for about an hour and 40 minutes. I would like to ask you how much more time do you have for us?
I mean, I think if you have a few more questions, yeah, I'm happy to take them.
Yeah,
Yeah, I
so
do have. Yeah. Sorry, Cecil. Yeah, I didn't mean to interrupt you. I just wanted to say that I have a general question. Can I ask that question, Cecil?
okay, go ahead. I have a question here from Mariana, but just go ask your question.
Yeah, you can ask that question. I will wait for my time, Cecil. Yeah.
Okay, so um, Mariana is asking, could the deviations that you have observed indicate something fundamentally new about how the universe has evolved since the Big Bang?
Um, I would say probably no, for different reasons. So the first one is that you've seen the image, right? There is a tension, let's call it, well, tension. Yeah, there is a discrepancy, let's call it that way. But it's not extremely significant yet. So it means that it's a small variation somehow. So we think if this were to be true, and not just statistical fluctuation, this could mean that indeed there are changes on how the universe evolved as a function of time. But it's important to keep in mind that the observations that we used go up to redshift 1 or so. So basically halfway, going back to the origin of the universe. To extrapolate what happened earlier than that, it's a bit dangerous in the sense that what we are measuring are things that happened in the last 7 billion years. If we want to go back to the Big Bang, that's 13 point something, depending on the model that you choose. Going from these 7 billion years to 13, well, it's not straightforward in the sense that there might be multiple ways of doing that. So I would say it's a bit, I wouldn't claim any change in the primordial universe from these measurements, because what we're really measuring here is what we call the late universe. So it's basically the last few billion years. What we could do, though, is to introduce additional information, additional measurements from the primordial universe, and try to basically measure these distortions combined information. And that could also provide information on different times of the universe. We haven't done that yet. But it's definitely interesting, yes. Yeah.
Thank you. So, yeah, I'd like to pass the mic to Agnostic.
Yeah. Thanks, Cecil. Thanks, Isaac, for taking more questions. So, with general relativity, we understand that there is a theory proposed that if a person travels at the speed of light, then and then once he comes back to the Earth, say for example, if he travels to a galaxy at the speed of light and then he travels back to Earth, then a lot of things would have gone past. People would have aged more than the person who had traveled to galaxy and has returned back. So this is the theory, but I mean, do you think this holds true for the biological aging as well, Isaac? Uh, what is your thought uh, on this one?
Yes. So basically, time and space are linked, and I mean, this is assuming Einstein was right. The difference between Newton and Einstein is that time is no longer an absolute quantity. Time is something that depends on basically who's measuring it, and it's linked to space. So indeed, if you travel very, very fast, time will slow down for this person that's traveling. I mean, it will not slow down for that person, but someone that's not traveling at the same speed will see that the time of the person traveling will slow down compared to theirs. And this actually has been measured on Earth. So basically, there are clocks that have been put in planes. They synchronize the clocks, and after a few, after the plane's been traveling for some time, they've checked, and there is a difference between the clock that was on the plane and the clock that was on Earth. So time really changes depending on the speed at which we propagate, and that should affect biological time too. Yeah. The thing is that the speeds that we can reach, I mean, with our technology, they are so small compared to the speed of light that any time variation is totally negligible. But theoretically, if we could reach speeds of the same order of the speed of light, yes, time would slow down.
I have just another question. Um, so we know that the mathematical models and the observations that we have made um, all conform to the theory of general relativity. And Einstein has even tried to explain, has given an explanation that we have to consider space and time as a fabric, and any larger mass would bend that space and time. Um, so this explanation, whatever he has given, um, so that is just an explanation, isn't it? Because his general theory of relativity conforms to all the observations and mathematical models that we have now. But could that fabric model be wrong, even though the general relativity might be? I mean, it conforms to all the models.
So you mean could general relativity be wrong? Is that your question?
Yeah, the time dilation and all those is fine, but how do we consider the space and time as intertwined? Uh, like as Einstein proposed that space and time is like a
Mm-hmm.
fabric where a larger mass body will bend that space and time.
Yeah.
Uh,
Um,
so just
I
just
mean,
just from a
yeah.
rational perspective, how do we? I mean, because I'm not a physicist, so it's hard for me to imagine whether the space and time would be intertwined as Einstein had explained. Uh, so it's difficult to imagine. Uh, but mathematically, it is just an abstraction, isn't it? All the mathematics, all the theories, they are all just abstractions. Um, uh, but I'm just wondering if, even though whatever general relativity is true, whatever he has proposed, but the model that he has proposed, that it is a space and time is a fabric, and the larger mass would uh, actually disturb that space and time.
Hmm.
It's difficult for me to imagine that. Yeah.
Yeah. So let me start by saying that it's not very intuitive. I mean, I guess that's why when Einstein introduced his theory, his peers, well, were probably not super excited at the time. It was, I mean, Newton's theory is much easier to understand in the sense that intuitively that's what we're used to because we live in the universe. I mean, around us, we just see our three dimensions, and time is something on which there seems we have no control whatsoever. So that just looks like Newton's theory. Then Einstein came and he proposed this, and mathematically, as you said, we can do many things. Mathematically, you can put as many dimensions as you want, and you can basically build very, very abstract models. But Einstein said, well, actually, the universe works like this. And I think the key point in this discussion is that till now, all observations that we've managed to do confirm Einstein's theory. And as I was saying, for example, at the solar system level, Einstein's theory works exceptionally well. So it means that basically this fabric of space-time and the fact that you have massive objects and they introduce perturbations to space-time, this works extremely, extremely well, at least at the solar system level. So it might be wrong. We know that, at the end, we are looking after this unique theory that could explain everything, ideally, right? And we know that general relativity and quantum mechanics are difficult to put together. So there might be something else. There might be a more, I wouldn't say better, but a model, a theory closest to how the universe actually works. But if that model exists, it would need to explain everything that general relativity can explain right now. So that's why it's difficult to go beyond general relativity. Because if you want to replace general relativity by something, you need to find something that general relativity cannot explain, and your theory must be able to explain everything that general relativity explained before. So that's why it's so hard to actually drop Einstein's theory and use something else. We haven't found anything yet in that sense.
Can I just add that in your observations, that delta between the curved line that you showed that represented Einstein's equations and your observations, if we zoom into that gap, I mean, we don't have to reinvent things till there, but that gap should guide us to see how we can explain that gap in some way.
I'm not 100% sure I got that. You mean in the figure when I show the predictions and the measurements, and that gap is the one you're referring to?
Mm-hmm. Yeah, exactly.
Right. Yeah. So that's why these measurements are exciting. I mean, it's not the very first time that we found some measurements that are a little bit discrepant with general relativity, but these are model-independent measurements. So there are very few assumptions that went into this analysis to get these blue points, and indeed we see there is a discrepancy. So this gap, exactly as you said, this can inform us on how we should start looking at models beyond general relativity that can explain these observations. But in addition to this, such a model will need to explain everything else that general relativity can also explain. And that's hard because general relativity works, except for cosmological scales, where it's what we're studying now. It works very, very well. So it's not an easy exercise.
I have another question. I thought of it. It's a general, but will CERN, in particle physics, with their models, could that help with this? And then obviously in the future, quantum, computers can help with modeling, and then I was wondering if quantum mechanics is affected by any of this. But if those subjects are too large, then you can just maybe I should have asked it earlier.
No, yeah, I mean, definitely at some point there is kind of an overlap with particle physicists. In cosmology, we try to understand things as a whole, but the components of the universe at the end are essentially particles. So there are some fields, for example, people that study dark matter, that actually you can do that by trying to detect dark matter particles or by trying to understand the properties of this component. And depending on what you do, you would do more from a particle physicist perspective at the Large Hadron Collider or some particle accelerators, or you would do it more from a cosmological perspective. Then computers will definitely help. We're relying very much on them now. And because these analyses are very computationally expensive. And basically, we need to use some of the largest supercomputers in the world to perform this type of analysis. And on top of that, we are now moving also to the use of machine learning and artificial intelligence to basically speed up the computations and help us perform the analysis. So this is very, very much linked indeed. Quantum mechanics, that's tricky. As I said, gravity and quantum mechanics don't really get along, and there is a very interesting field of research trying to put the two of them together. But I wouldn't dare commenting about that. That's quite far from my expertise, and I'm not really aware of the latest developments in the field.
Dr.
Yeah,
Isaac,
thank
what's the best way to get in touch with you for research purposes?
I think I put my email in the first slide. Let me quickly check that because I forgot. Yes, in the first slide that I think Cecile shared here in the room, you can find my email. Just feel free to send me a message. Happy to discuss.
Okay, thank you.
Yeah, Isaac, I would just like to ask you, do you have any existing papers wherein you had been using artificial intelligence?
Um, not, I mean, I might have been involved a little bit in some of them, but not really. I haven't really used this much on my research. But there are other cosmologies that use machine learning quite a lot. I would say it's something that 10 years ago, I mean, it existed obviously, but was not used significantly within the community. Things are moving now, things are changing, and people are starting to use machine learning quite often in different parts of the analysis. Personally, I think I do not have any paper, but if you look for machine learning and cosmology, I'm sure you'll find plenty of different scientific articles discussing this type of analysis. It's a bit tricky because it combines both the cosmology, so you might need some knowledge on cosmology, and also all the machine learning. So you might need some understanding on convolutional neural networks and all the different types of systems. But it's definitely interesting, and it's growing on interest recently.
Yeah,
Well,
thank you. The reason why I'm asking because I have another platform dedicated basically to artificial intelligence, and if you have a paper, I would like to invite you to speak regarding that matter. Actually, there are new tools that are coming, and I think the people of Caltech and NVIDIA have these neural operators, which are physics designed operators that can be used for research in various forms, maybe to predict the weather. And I think they are also trying to use it for medicine. And I think they are trying to design something for cosmology. And yeah, and there is also Sakana AI of Japan, which is actually trying to focus on research. So I was just thinking about that because we are trying to use those tools more and more, just like what you said, to enhance the data that you're observing, and also maybe to model the theories that we have. And
Mm-hmm.
it's pastor. So yeah, I was very curious. On the other hand, as regards quantum computers, yeah, for now there is still no useful open and close quotation for useful quantum computer that we are using. It is still very difficult, but who knows, there might just be a sudden snap at a certain time, and then we would be able to make use of it, and maybe people are still using more supercomputers because quantum supremacy has not been displayed yet. There is a lot of noise that has to be treated by quantum error correction. So yeah, I was just asking about that. In the future, I'd like to invite you in our event if you have some research involving
Mhm.
AI. However, I would like to invite you again here in the near future in Quantum Photonics. It has been a great discussion, and we have a very patient teacher here, teacher researcher, and I'd like to thank you, Isaac, for answering all kinds of questions and making this open forum also very interesting. So I would like to pass the mic to you now, Isaac, if you have some last messages to the audience because we're near the top of the hour.
Yeah, no, I just wanted to thank you again for the invitation. I think it's been really fun. I've enjoyed all your questions, and I think it's been a very nice and useful discussion. Um, yeah, I just hope that you found this cosmology topic interesting. And as I said, there is my email in the slides. So in case you want to keep discussing, I'm happy to reply to your messages if you have any questions. And yeah, I think that's all for me.
Yeah, thank you so much, Isaac. We really, really appreciate, and I hope we can invite you for your future papers or yeah other topics because there are a lot of good researchers. But the thing is, how do you impart knowledge to the audience? How do you explain? How you bring science nearer to the people? And this is our objective here in quantum photonics. We are trying to make science more interesting and more reachable to the general audience. And yeah, you are among those people who's able to explain very well. So thank you. I'd like to ask Bob now if he has some comments before we close the room.
Well, yes, thank you, Cecile. I wanted to express appreciation for your slide deck, which helped a lot. These are difficult concepts for me, and I'm walking away with a bunch of stuff. Uh, so I thank you very much.
Yeah, I also want to say that yeah, I will send you, Isaac, when the YouTube, when we are able to have the edited version of Bob in YouTube, so that your slides are synced through what you're talking about. And by mentioning the slide numbers, it was a very good guide for Bob to be able to transcribe it in the YouTube channel of Quantum Photonics. So now, yeah, however interesting our discussion, we have to try to wrap up. And I'd like to thank people who came up on stage and also those who were not able to come up. I think there were still 3 people whom we could not bring on stage. And yeah, thank you so much for your participation. And also those here on stage, Agnostic, Kevin, and Ash, thank you. So I'd like to give the mic now to Darcel to help us do the countdown to close the room.
Thank you, Cecile, and thank you, Isaac, for a wonderful talk. Um, Very interesting. To close the room, we're going to start our countdown from lucky number 7. Is everybody ready?
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 7.
7,
7.
7.
Ash 6.
6,
Kevin 5.
5. Happy holidays.
Agnostic 4.
3.
Bob Thrace.
3 it is.
Cecile Dos Eques.
Dos Equis.
Isaac, you're number 1. Call out our last number, please.
1.
Thank you so much, Isaac.
Thank
Please come
you.
again to Quantum Photonics soon. And to everyone, just check out our platform and see the next rooms that are coming. Thank you. So happy holidays.